Talking about potential energy today. Potential energy is the energy possessed by a body by virtue of its position or configuration. When we use the word position, we are meaning how much height does it possess from the ground level. And when we say configuration, we are talking about its compression or expansion, that is how its configuration has changed. For example, a stretched rubber band, a spring, string of the bow, etc. possesses potential energy. Other examples of potential energy are water stored in a dam has potential energy due to its position at the height. Remember, when we use the word position, we are meaning height from the ground level. A stone lying on the roof of the building possesses potential energy due to its height, while a wound spring of a watch has potential energy due to its shape or configuration. All the elastic substances like a spring, an elastic, a rubber band, a stretched bow, etc. possess potential energy due to their configuration. That particular kind of energy, potential energy, is known as elastic potential energy. If you look into the diagram given here, we can see on the left hand side, an object is reaching a certain height h through a straight path. Let us call that path 1. And on the right hand side, an object is reaching the same height through another path B, path 2, which is not a straight path. Since both of them are reaching the same height, the work done in both the cases or energy possessed by an object in both the cases is going to be the same, that is mgh. That means the potential energy does not depend upon the path followed during reaching that height. Path 1 is a straight path, path 2 is a crooked path. Still, potential energy possessed by both the objects is the same since they are reaching the same height h. Again, potential energy does not depend upon the path followed. It only depends upon height. Elastic potential energy. Elastic potential energy is the energy possessed by a body in a deformed state due to the change in its configuration. Like we had a talk, it is possessed by any kind of elastic substance like a spring, a rubber band, and elastic band. So, for example, energy possessed by a compressed or an elongated spring is elastic potential energy. We come to principle of conservation of energy or law of conservation of energy, an important law, the basic law of physics. It states that energy can neither be created nor be destroyed, but it can only be converted from one form to another form. This is one of the fundamental laws in physics and is applied in all the processes taking place in the universe. So whenever energy in one form disappears, an equal amount of energy appears in some other form. Thus, the total energy of the system remains constant. We shall be proving this conservation of mechanical energy for an object that is in free fall. So we consider here an object of mass m which is lying at a height h from the ground level at point A, and we are slowly dropping it. That means we are allowing it to fall freely under the action of gravity. As the body falls gradually, its speed or velocity is going to increase because the gravity is pulling it downwards. Now, when the velocity is increasing, the kinetic energy will automatically increase because Ke is equal to half mv square. At the same time, an equal amount of potential energy will keep on decreasing because potential energy is equal to mgh and height is decreasing. Remember, as velocity is increasing, height is decreasing. So, as kinetic energy is increasing, potential energy is going to decrease. In short, total energy will always remain constant. So, we consider the free fall of an object at three positions. At position A, when it is held in the hand, at that place, its velocity is 0. We consider its second position somewhere midway at point B, where we take its velocity to be v. And at the end, when it is striking the ground at point C, we take its velocity to be v dash. The distance through which the object is falling is from A to B, it is falling through a distance of x. So, distance from B to C will become h minus x because the total height from the ground level is h. We shall calculate the total energy at point A. That is when the body is at rest, it is held in the hand. Since it is held in the hand, it does not possess any velocity and its kinetic energy is 0. However, it does possess a height h, so it has a potential energy mgh. If we add them both, we get the total mechanical energy that will be equal to 0 plus mgh. So total mechanical energy at point A will become equal to mgh. At point A, this was all calculation at point A. We are going to do the similar kind of calculation at point B. Let us check point B again. At point B, the velocity of the object is v and its height from the ground level is h minus x. We have two things to consider, its velocity and its height. So height from ground level is h minus x while the velocity is v. Let us calculate. So its velocity at point, taking the velocity to be v at point B, we are calculating first its kinetic energy. At point B, suppose the body falls freely to a height x and reaches the point B with velocity v. So we use the equation v square minus u square is equal to 2as, the third equation of motion. We put u to be 0 because its initial velocity was 0. A will become g because it is in free fall. And s, that is distance, will become x because it is falling through a distance x. So we get v square is equal to 2gx. Now we calculate the kinetic energy. Kinetic energy at B is equal to half m v dash square, v square, that is equal to half m. For v square we will put 2gx. So half m into 2gx. 2 will get cancelled out. We get mgx. That is kinetic energy. Now we calculate potential energy. Potential energy is equal to mg. Instead of h, we will use h minus x because at position B, the object is at a height of h minus x from the ground level. So we get mg h minus x. Now we add this kinetic energy and this potential energy to calculate the total mechanical energy. So total energy at point B is equal to kinetic energy plus potential energy. Remember, potential energy is often showed represented by the letter U. So we get mgx plus mgh minus x. When you open this bracket, you multiply mg with h, you get mgh minus mg with x, that is minus mgx, plus mgx minus mgx will get cancelled out and you are left with only mgh. So you get the total mechanical energy at position B is mgh, which is exactly the same as total mechanical energy at point A. See, at point A, mechanical energy was mgh. And at point B also the total mechanical energy we are getting to be is mgh. Now we consider at point C. Let us see what happens at point C. At point C, the object is touching the ground, so its height becomes 0. When its height becomes 0, potential energy automatically becomes 0. But we still have to calculate its kinetic energy. Let us move ahead with the calculation at point C. So at point C, suppose the body finally reached at point C on ground with velocity v dash. Again, we use the equation v square minus u square is equal to 2as. Instead of v, we are using v dash for point C. U will be 0, A will become G, S will become H now because the object has fallen through the full height H. So we get V dash square is equal to 2GH. We calculate kinetic energy at C, that is half m V dash square, that is half m into this V dash square, that is 2GH. So 2 gets cancelled out, we get mgh. And potential energy is 0 because height becomes 0. It is touching the ground, so h is 0. Hence, potential energy is equal to mg into 0, that is 0. So if we calculate the total mechanical energy at point C, we get E is equal to PE plus KE. Potential energy is 0, while kinetic energy is mgh, and hence total mechanical energy at position C is also exactly mgh. Thus, we can say that the total energy of a freely falling object is conserved. So, what is happening? All the potential energy that it was possessing at point A, if you look carefully again, at point A, its height is maximum. When height is maximum, it possesses maximum potential energy. While kinetic energy is 0 because it does not have a velocity. We are holding it in the hand. V is 0. So KE is 0. While at point C, PE is becoming 0 because height is 0. While kinetic energy is becoming maximum. So all of the potential energy at A has converted into all of the kinetic energy by the time the object is reaching point C. Thus, one form of energy has converted into another form of energy, which is law of conservation of energy. And we have proved that the total mechanical energy of this free falling object at every point is coming to be exactly mgh. At point A, mgh, at point B, mgh, and at point C as well, it is mgh. We just proved in mathematics. Thus, as the body falls, its potential energy decreases and kinetic energy increases by an equal amount. Thus, its total mechanical energy remains constant at all points. Thus, total mechanical energy is conserved during the free fall of the body as shown in this diagram. You can see the diagram. It shows how potential energy is increasing here. Simultaneously, kinetic energy is decreasing here, or vice versa, but total energy of the system remains constant. Hence, we get a straight line at the graph. That is how we prove law of conservation of energy for a freely falling object.